Welcome back. Today we're going to talk about Le Chatelier's principle. Let's bring out Le Chatelier. We gotta look at the guy. Oh, hello, Monsieur Le Chatelier. Look at his nice little mustache and his good hair. I like his glasses. Oh, his name is Henri Louis Le Chatelier. Oh, very nice. You gotta get out of here. I'm intimidated by his eagle stare. All right. So, Le Chatelier's principle tells us that if we do something to disturb a system in equilibrium, the system responds in a way that partially counteracts what you have done. This is a key word here, partially counteracts. It means that it does not counteract it completely, but it does what it can to reset the change. So it's a conversation on what I like to refer to as stress and response. You've probably heard the expression in your life, the idea that like every reaction has an equal reaction. Le Chatelier's principle is kind of the chemistry version of that, where if we have a system at equilibrium, it would like to stay at equilibrium. So if we do something to take it out of equilibrium, it will respond in such a way to actually get itself back into equilibrium. This is kind of a hard concept to visualize, but it is something that happens while we are in equilibrium. So we have three possible causes of disturbance. We are going to talk about two today. The ones that we're going to talk about today is a change in concentration of the reactants or the products and a change in temperature. Tomorrow, or at least in the next video, I guess I should say, you are going to be discussing the size or the volume of the container. That is only applicable to gaseous systems. It will not be included in this video. It will be included in the next one. So in this one, we're only talking about 1 and 2. 3 is specifically for gases. So let's dive right in. Let's talk about concentration disturbances. So when we're talking about concentration, we have to think about it. Let's first think about it in the form of rate. I think that's kind of the easiest way to relate what we know to what we can learn now. So based on rate and our knowledge of rate, what would happen if we added more A to the system? So I have two different columns here. I have like what does the equilibrium look like initially when we add more A, and what does equilibrium look like after it has reestablished itself? So if we increase the amount of A, what does that increase? Maybe pause for a second if you have to and think about it. Well, it increases the amount of A, but it also increases the rate of the forward reaction, not the reverse reaction. It doesn't even decrease the reverse reaction. It simply increases the rate of the forward reaction. So we have the forward reaction, which is all sped up, and then I'm going to draw my reverse reaction about the same size as it was before. So just understand that we have no change to the reverse reaction, but we are increasing the rate of the forward reaction. Let's rewrite our products or reactants down here. So this is A plus B, C plus D. I know that there's supposed to be coefficients, but I'm not really worried about it right now. So what happens after equilibrium has been reestablished? Well, what happens is that we get a new equilibrium, but this time it's a little different. I mean, I'm trying my best to illustrate this to show you that the equilibrium has changed, although it has reached equilibrium again. So let's think about what this would look like, on a regular level. So if I increase the amount of A, then that means that there's more A to react with B, which means that I'm going to increase the amount of C and D. That makes sense, right? But if you think about it, the more that I increase C and D, the more I push back the other direction. So the more that I increase C and D, the more that I push back. So there is an opportunity that eventually I'm going to use up all that extra A, not all of the extra A, but some of it, and I'm going to get back to equilibrium. This is how we would look at it through rate. And if we were to look at this through the lens of Le Chatelier, we are talking about stress and response. A has increased, which has disrupted equilibrium. So what can we do to realign equilibrium? Well, we can shift towards the right side, and that's what we're going to do. The system will shift towards the right to counteract the disturbance. This changes the amount. This is kind of like what we were talking about before. If A is increasing, let me do this in blue actually, not red. If A is increasing, then the amount of B is going to start decreasing. That only makes sense, right? Because we're putting A in, but not any new B. So B is just going to start going down. In order to respond to this, right, we have this side of the equation's going out of control, right? A is reacting with all this B. We're running out of B. In order to fix this, we have to produce more B and produce more A. The only way that we can do that is by increasing the amount of C and increasing the amount of D. So again, it's about stress and it's about response. So let's look at what this does to concentration. If we have the amounts increasing for each, it makes sense that the concentration would increase just as well. So A goes up, B goes down, C goes up, and D has no change. Now you might be thinking to yourself, why the heck doesn't D have change? But you might not have looked at the problem thoroughly. If you look on the problem, it says that D is a solid, and solids do not have a concentration. So it does not matter how much we add, it does not increase the concentration of D. It does not mean that the amount of D doesn't increase, it just means that the concentration doesn't change. What would this have the effect on the KEQ? Let's take a second, let's write the KEQ expression. So this would be something like C squared over A times B. Now as, let's say like C is going up, A is going up, B is going down. But honestly, none of this really matters because K is only affected by temperature. Is adding a temperature change? No, it's not a temperature change. So that means that K does not change. Not change. All right, so again, K will only change if there's an effect on temperature. Let's look at a different stress. What would happen if some of the B was removed from the system? So let's think about equilibrium again. Let's say that we have A plus B, and on this side we have C plus D. So now I am removing B. So what does that do to the forward reaction? Well, it's going to decrease the rate of the forward reaction. Is it going to have any effect on the reverse reaction? No, not really. But it is going to decrease the rate of the forward reaction. Now, after equilibrium has been reestablished, we're going to have something very similar to what we had last time, but this time our equilibrium maybe is going to be a little different. It's not going to be as large as it was before. Those arrows are supposed to be equal. I'm just a goof. And then we are reestablished at equilibrium. Okay? But let's think about this through the lens of Le Chatelier. The stress is that I'm losing B, which means that one side of my equation is falling down. What can I do to support that equation? I have to go over to that side and push it back up. So what side am I going to shift to? I'm going to shift to the left. Because if I shift left, then I can increase the amount of A while the B is decreasing. And if I increase the amount of A, I'm also bringing up that side. In doing so, I'm going to decrease the amount of C and decrease the amount of D. So it's not really about bringing this back up, it's more about bringing this side down and this up at the same time. So it's kind of like, meet me in the middle, right? Partially adjust. And if I'm thinking about this in the lens of concentration, then it's going to be very similar to what I saw before, where the amount or the concentration of A is going up, excuse me, that was a mistake. The concentration of B is going down, C is going down, and D has no change. And removing B is not a temperature change, so there is no change to K. Maybe you can notice a generalization here. Maybe not. Let's look forward until we can figure this out, but maybe you might notice that there is a pattern emerging here between increasing and decreasing and what direction I shift. We'll see if you pick it up as we keep going. So let's talk about disturbances in temperature. So in this situation, we now have energy included in the equation. And I want you to think about it. The energy is on the right side, which means that the forward direction is an exothermic reaction, but the reverse direction is an endothermic reaction. One releases energy, the other one is dependent on it. It's kind of interesting to think about. So what would happen if I turned up the heat, if I increased the temperature? I want you to think about energy as just another substance that's part of this process, just like A, B, or C. If I increase the energy, what is that going to do to the overall reaction? Just like with rate, if I increase the concentration of something, I increase that reaction. If If I increase the energy, I'm going to increase the reaction in that direction. So if I'm thinking about this, I'm actually going to increase the rate of both reactions, but which reaction am I going to increase the rate of the most? It's probably going to be the reverse. So the reverse reaction is going to really speed up, and the forward reaction is also going to speed up, but just not as much. So after equilibrium, this is A plus B, C plus D. After equilibrium has been reestablished, I'm going to have a much greater rate for both reactions, but I am going to reestablish that equilibrium. So remember that this is about stress and response through the lens of Le Chatelier. The stress is that the temperature went up. What can Le Chatelier do to decrease the temperature? Remember that one of these reactions is exothermic. The forward reaction is exothermic, which means releasing heat. So if I want to release heat, I have to shift towards the forward reaction, which means I'm going to shift towards the left. So if I shift left, I am going to then successfully decrease energy by increasing the rate of the exothermic reaction. So the amount of A and B is going to go up, the amount of C and D is going to go down. Notice that in this one, it's simply a direct relationship between the direction that I shift. If I shifted to the left, everything on the left went up, and everything that on the side that I shifted away from went down. That's very interesting. Let's see if that pattern consists. Or persists. I don't know why I said consists. All right, anyways. What happens if we look at the concentrations? So just like before, the concentrations are pretty much directly related to the amount. These are going to go down. D is going to have no effect. I think I wrote no change before, but here we are. Now let's think about K. So before I said that K can only be affected by a temperature change, and here we are at a temperature change. So if I write my K expression again, I have A and I have B, and we're saying that the concentration of C is going down, but the concentration of A is going up, and B is going up. So what's going to happen to the overall change, or is K going to change in any way? So think about it for a second if you need to, while I casually flip to the right page. In this situation, K is going to decrease, because as our denominator is getting larger, our numerator is getting smaller. That means that K overall is going down. So what happens if we decrease the temperature? Let's think about this one more time. Let's think about it through the lens of rate. If I decrease the temperature, if I have A plus B and C plus D, and I'm going to put energy on this one just so I can visualize it again. This time energy is going down. The reaction is getting slower in that direction, right? The reaction that requires energy is losing its rate. So that means that my forward reaction is going to slow down. Let's kind of draw this a little better. My forward reaction is going to slow down because, just a decrease in temperature is a decrease in temperature, but also my reverse reaction is going to decrease. And after I reestablish equilibrium, I have A plus B. I'm going to have a new equilibrium that's going to be a little smaller than it was before because now I have a lower temperature, C plus D. Now, how does this work through the lens of Le Chatelier? Remember that the stress is that the energy is going down, which means that the reaction is getting colder. What can I do to increase the energy of the reaction? What can I do to increase the energy? Did I say that? I think I just said the same thing twice while I was thinking. Either way, I'm going to shift to the right. So I'm going to shift to the right, and then if I do that, I'm going to increase the amount of everything on the right side. So A is going to go down, B is going to go down, C goes up, D goes up. And again, this makes sense from the perspective of Le Chatelier, because as energy goes down, I want to shift over to the side that requires energy, so I can get back going and I can increase the temperature again. So if we think about this through the lens of concentration, then we are going to have a decrease in the amount of A, decrease in the amount of B, increase in the amount of C, and no change. I think I wrote no effect on the last page, but here we are. So I'm having an increase or a decrease to the side that I'm shifting towards. And K overall, if we write the K expression again, it's always good to just practice it because it's kind of fun to write it. A, B. Then we have an overall increase in C, decrease in A and B, which means that my K is going to increase overall. And in a summarized way, that is Le Chatelier's principle. Did you pick up the pattern? I don't know if you noticed. Let's go back to one of the examples and let's see if you can suss out the pattern. So we have A plus B gives us C plus D, and then we're also going to include the energy thing. But I want you to realize that there is a pattern happening here, and I don't want you to rely so much on the pattern in the sense that I want you to memorize anything, because I'm not a big memorizing kind of person. I want you to analyze and understand why these changes are occurring. But sometimes we're in a mood, and we just kind of need to figure things out, and there's always something that you can rely on based on this pattern to kind of help you through stuff when you're talking about Le Chatelier. Excuse me. So let's think about our first example. In our first example, I increased A. In what direction did I shift? Based on Le Chatelier's principle, I shift to the right, which means that I increased C and D, and I decreased B. Okay, let's keep thinking. What happened in my other example when I increased or I decreased B? In my other example, when I decreased B, I shifted towards B, which made me decrease C, decrease D, and increase A. Okay, that's very interesting. But what happens when I increased energy? This might be when the pattern reveals itself. When I increased energy, I shifted towards the other side, which made me increase A and B and decrease C and D. Have you picked up the pattern yet? With Le Chatelier's principle, whenever I have an increase in something, equilibrium will always shift away from the increase. The side that I shift to will always go up. The side that I shift away from will always go down. What about a decrease? Well, as you might have noticed from the pattern, when I decreased my energy, that also made me shift towards the decrease, which made my D go up, C go up, B go down, A go down. So with a decrease, when I have any sort of decrease to the system, I shift towards the decrease. Again, this is just a pattern. It's not the whole picture. Please make sure that you understand both concepts, not just the pattern itself. And that is Le Chatelier's principle. We'll see you next time.